Paulus, who's the lead research scientist at Salesforce, and he's been doing research in natural language processing and working with extractive summarization. So could we give a warm round of applause and welcome Romain.
Hi. Thank you so much for coming here today. I'm excited to talk to you about some of my work at Salesforce Research, as well as work done by some of my colleagues and other research groups that I think is very influential in NLP using deep learning. So a little bit about myself. So I'm a research scientist at Salesforce Research. I've been doing this for the past year and a half for now. I work mostly in sequence-to-sequence learning, like abstractive summarization, and my whole research group also tries to do NLP and deep learning in other domains like speech, computer vision, and the intersection of all these things. Before that, I was a lead developer for MetaMind, a deep learning as a service startup, where you could upload your image or text data and then train classifiers with that, even if you knew nothing about deep learning. So that was pretty fun to do for a couple of years. And even before that, I was doing my master's in France at ISEP in Paris. So some of you may be familiar with deep learning for NLP. Some of you may have just vaguely heard of it. So I'm going to try to keep this talk pretty high level. And if you have more questions about like go details of models or other things related to that, feel free to go later after the session and ask me anything. So you may have heard about how deep learning is used for NLP. And even if you don't realize it, you may have even used systems that use deep learning for NLP in your everyday life. Some of the most famous ones are automatic translation for almost any language that any of us speaks in this room today. Something that's even a bit more ambitious that we can start to see is AI writing complex legal documents for lawyers, as we can see here. And if you've used Siri or Alexa, they are using more and more deep learning as well. Even though when Siri was started, it didn't always use deep learning, now we can see that it's actually one of the best ways to get a very good performance assistant. And as well as summarization and very simple things like grammar checker can also be improved with AI, as we can see. So how did we get here? Like, why did we actually need deep learning for all these things? Well, if we go back at the beginning of the history of AI, NLP was one of the first things that we tried to automate. Like, if you look back at the Turing test, this is exactly what you're trying to do. We're trying to make computers that can provide English outputs, understand human language, as well as humans do. And so the first approach people were trying to do in the 50s and 60s was to look at grammar rules and meaning of words that we all know because we have classified it in books, and then encode that into a computer software, and in the hopes that given these rules that we know are the true rules of English, we will be able to get a program that will understand human language and even do translations, since we also know exactly how to translate words as humans do. The problem with this approach is that the rules are not as hard and as set as we think they are. It's hard to encode every single rule of a language. Like, we twist the grammar rules every day, even if we don't really realize it. And some are actually quite subtle and complex to encode. If you look at this very famous example, you can see two sentences that are very similar, but only differ in one very particular word at the end. But that change of the verb, fear, to advocated, actually changes who they, in bold, refers to in the sentence. Try to encode that with your own rules and tell a program how to understand difference. It's going to be very hard. And so this is only one of the many rules that are hard to disambiguate. Another thing to take into account is that languages evolve all the time, and the rules can mean different things depending on the context as well. Like, for example, there is no definition for emojis in dictionaries, but still, this is something we have to understand, and we have to understand how they change meaning if you want to have a system that does well in English language. And in the end, we do have grammar rules for very common languages, but if you try and study a new language that you've never heard before, do we actually need a grammar book? Can we just use like raw data? And it turns out with the rise of machine learning, this is exactly the approach we've been taking. Instead of starting with a very defined set of rules, we start with raw documents here. One thing to keep in mind is that computers, as you know, cannot read text, they only read numbers. So one crucial step here that has been bothering scientists for a while is how to convert this text into words, into numbers. But once this step has been done, you can actually use these numbers and train models that will perform very specific tasks only based on examples they've seen. And this is how for a long time we've been training models to do machine translation. Here is one example of what's called a phrase-based machine translation system that has been the state of the art for a long time, where from data we learn how to rearrange words from one language to the other, and also learn how there are different possibilities to translate some words into others, because as we know, you can differentiate, depending on context, different translations. And you can use that approach for other tasks like sentiment analysis, which is here an example where you have examples of, let's say, documents or customer reviews. Some express good feelings, some express bad feelings, and you want to know what makes such review particularly positive using the words and looking at how the different words come into play. And so this approach has been dominating the NLP field for a long time, but it also has some drawbacks. As I mentioned, you need to translate your documents into numbers, but for a while we didn't have the computing power of using the whole sentence, nor the models that will be able to make subtle differences between the words depending on the order. That's why some of the simplifications called feature design were stemming the words, where you remove the ending of the word to only get the root of it to have the meaning. Also bag of words, where you don't take into account the word order, only take into account which words or which sequences of words appear, hoping that it will give you enough meaning to make a decision on the sentence. And one other drawback of this approach is that you only learn one representation for every word, but what if you come across an entirely new word that you have never seen before? In most cases, your model has no idea how to make use of that word. And so keeping these two limitations in mind, the advent of deep learning is really what helped us break out of this cycle. And it really started to take off with the advent of word embeddings. So some of you may have heard of word embeddings. It is a way to represent words that encodes different aspects of their meaning across different dimensions. So you may have seen this very famous example where you have word vectors representing king or queen and women, and you can see that this is learned completely without supervision. And you can see that it learns what is the relative relationship between a king and queen, that the gender is different, and that if you change the age, it also becomes princess as well. So what's very amazing is that you can learn all these representations not by telling the computer, put the royalty information here and put the age information here, but this is learned completely from context with no supervision, which means that if you have new or rare words, you can try to find the closest word vector to them based on the context that you have, which means it's a very flexible way of representing your input. And that circumvents the issue we had before, where we had to make simplifications on the input to translate it into numbers. Here we can take the whole sequence without having to reduce its meaning or its information. So once we have these word vectors, we can actually train completely tasks from end to end. And this has been done traditionally with the sequence-to-sequence learning framework, also called Encoder Decoder, where here you start with the words. This is the embedding matrix that we have described before. And so at every time step, you look at the words one by one, and you compute an intermediate representation for the whole input sequence. Here, everything here is a vector, and everything here in between these steps is also a vector. This is computed by what's called a recurrent neural network. So which means that in the end, you have a single vector that represents your whole input sequence. And from that, depending on the tasks that you want to solve, if it's either machine translation or here question answering and dialogue, you can tell that representation and use another decoder network to output the words one by one that you expect the model to do. And so there are various ways to train this, but as long as you have the whole network differentiable, this can solve most of the sequence-to-sequence tasks you've seen. So one of the applications of such network, and one I've been working on for a long time, is called summarization. So why summarization matters? If you've been on Reddit, you may have seen this user, AutoTLDR, that actually summarizes every news article that gets posted on the site automatically. So here it does it in a way that's called extractive. Now I'll go back to that later. But summarization is not limited just to the content of news articles. You can also generate bullet points based on the content as well, which is here what websites such as Daily Mail or until recently CNN were doing. And you can actually train deep learning models to do both of these things. You can summarize other things than just news articles, but I'm going to skip on that domain right now to illustrate the challenges and the solution we can take to solve them. So as I mentioned, there are two main ways to solve summarization. You can take an abstractive approach or an extractive one. Abstraction is mostly what humans have been preferring. When you want to summarize something and tell your friends about it, you're rarely going to do copy and pasting of the original text unless you are not sure you completely understand it and don't want to misinterpret what has been said. But we usually use either new words or new phrasings to summarize something as humans. And we can let computers do the same thing, but it's harder to automate because if you give your model more flexibility, they have more opportunities to make mistakes. So a safer option is to use an extractive approach. It's more robust. It only takes into account the words and the sequences of the input article, and you just highlight the parts that you think are the most relevant, and then construct a new summary based only on the words you've highlighted. So it is obviously less flexible, and it cannot represent every single summary that humans have created. But given these two frameworks, we're trying to tackle the most ambitious of them, the abstractive summarization, with the following model that we call the end-to-end abstractive summarization model. So if you look, this is very similar to the Encoder Decoder framework that we've shown before. Here you encode your news article, which can be like 800 words long, into a sequence of vectors and single vector at the end. And here we had an extra step on top of it called attention. The reason for this step is that the longer your input sequence is, the harder it becomes to represent it as a single fixed length vector. So when you decode, when you generate your summary words one by one, you're actually going to focus your attention on different parts of the model depending on which kind of facts and which entities you are trying to summarize the most. And since the summary can also get very long as well, we have attention both of the input sequence and on the output sequence as well here, at least considering the words that we have generated so far, not the future words, of course, which we don't have access to at this point. So that's a work that we have done with my colleagues last year. And so when we train this with the standard recurrent network training algorithm called teacher forcing, we start to see some issues in long-term coherence and repeating phrases in the decoder. And the reason is because the way these are trained most of the time is you use local supervision of the words to tell your model whether one specific word was the right one that you wanted to have in the summary. Because remember, we have access to human-written summaries, and this is how we want our model to be as close as we can to them. So which means that in the end, for sequences of like 10, 15 words, the model was coherent, but when you start to go longer to like multiple sentences, it wasn't as coherent as we hoped. So instead, we came up with a way to train the model with reinforcement learning using a global reward to give the model a feedback on whether the entire summary was good enough or not. So this reward that we use is called the Rouge score, and that's a score that actually was used very often to evaluate how summaries correspond to a ground truth that a human has written. And they usually go from 0 to 100. 0 meaning none of the words in your summary are the ones that the human has written, and 100 means this is exactly what the human has written. In practice, you're never going to have Rouge scores of 100. If you ask two humans to summarize the same news article, many of them will give you different answers, but they will both be valid. So the score, the reward we are using has to take this into account to make sure that we give some good feedback to models that give some good words, even if the entire sequence is not the same one. And so once we combine these two approaches, we can actually have a model that performs quite well to generate multiple sentences for a news article. So this shows one of the articles that we've summarized. In blue and green is the attention mechanism at each time step, which shows which article words our model is focusing on, and then which summary words also focusing on to not repeat itself. So this was pretty, this had a state-of-the-art result on summarization in CNN Daily Mail at the time, if you look at the Rouge score. But we're not completely happy with this because it had still a few main flaws. We realized that even though we allowed the model to generate any word it wants virtually, it could be as abstractive as we let it be. In practice, it still fell back on mainly extractive approach. And we looked into that and we found out the reason is because just copying the input words is still the safest way for a model to get a relevant summary. So we have to force the model to take more risk and to look outside of its comfort zone to get not only a summary that's correct, that has the right words, but one that's more abstractive than it could be by default. And this has led to the model that my former intern Wojtek Kruszyński and I just submitted to MNLP that we're going to present in Brussels next month. And so this is very similar to the previous one we've seen. However, here in the decoder part, we have an extra language model. So a language model, for those who are not completely familiar, in this context, takes as an input a sequence of words in a text and tries to predict the most likely next word to come after. And so in this context, we have trained the language model to model what summaries look like. And the idea is that using this in the decoder to generate summary words will let it generate words based on what a summary should sound like rather than copy words from the input. We realized it did improve abstraction a little bit, but we still needed one more thing to really push it forward, and that was using a new novelty score reward in reinforcement learning to not only reward the words that appear in the summary that human has written, but to reward if these words do not appear in the article or if the sequence of words doesn't appear too. And so based on these two innovations, we can see that our summaries are indeed way more abstractive than previous approaches. Like here you can see on the top, these are the first few words of a news article. Next line is what a human has written as a summary for these words. Yes, I have a question.
What you just said, did you say that your reward function is also composed of words that are not within the original input?
That's the reward function, yes. It rewards words that appear in the human summary but don't appear in the article. Yeah. Mm-hmm. So here we show two approaches of other similar models to the ones we've shown before. And then the last one is our new model. And in yellow, these are the words or the sequences of 3 words or more that are taken straight from the article. So we can see less yellow equals more abstractive. So we have clearly made improvements on that. And to illustrate even better the relative gains we had from these two changes, which are the language model and the novelty score, we tried to plot different variants of our model with a baseline here in orange, where we just replace words at random in a summary to make it more abstractive. And we can see that it's hard to have both a good Rouge score, which means a good relevance, and a good novel unigram score, which means a high abstraction. But as we can see, the last model, which is the final one we had, obtains the best trade-off in Rouge score versus abstractiveness. And so there's still a lot more work to be done in summarization. Namely, even though if we have improved abstraction, there are still fairer cases that our model has in which we can clearly see it does not look like a human has written it. And so having summaries that are virtually indistinguishable from human summaries is still a work in progress and an open research area, especially if we take open domain summarization or very long summaries. In addition, one step further will be to summarize many documents into one summary. That's called multi-document summarization. It has gained less attention because there are less trained data sets for this, but it's also in very high demand, especially if you consider that you want to summarize chains of emails or conversations or lots of customer reviews into one. That's going to be in very high demand by companies. Third, we've only focused on news articles at this point, but we also at Salesforce had people who were very interested in summarizing long, technical, pages-long documents, and that's still out of reach for us at this point, especially when the documents are like very complex and need an expert to understand. We need more research on that as well. And the final, which is actually related to the technical document one, is how to generate personalized summaries, especially depending on your level of knowledge as a reader about a particular topic. You might want to see different summaries, and that's still something that needs to have more research. So that's one of the examples you can use for NLP in deep learning. But that's still a very limited domain, like just summarization. There is a lot more going on in deep learning and NLP. And so that's why we think one of the main ways to reach general AI when it comes to language is to do multitask learning, which means you're trying to solve many tasks at once in the same model. So there are actually different kinds of multitask, and I'm going to just disambiguate here. You can do transfer learning, which is actually when you train a model on a first task and then reuse some of the representations of that model on another task that you want to improve, which means in that case you only care about the performance of the subsequent task. In practice, learning word embeddings, as I've showed before, is such an example. You train word vectors and then you can reuse them later to improve translation or summarization. And this has been an approach in other domains, like in the computer vision world. If you're familiar with this is what ImageNet pre-training is. You take a whole big network that can differentiate images and put them in 1,000 different classes. And then you can reuse that network that's pretty heavy and pretty big in subsequent tasks in which you may not have enough training data to help kickstart the model. But here we really care about true multitask, which means we want to have lots of different tasks, sometimes related, sometimes not, and we want to push the joint performance of all of them at the same time. And so this is, for example, what multilingual merchant translation would do. If you want a single model that can translate between different languages without having to train different parts of the model. And so this is a challenge, especially if the tasks are not related, because if you look at the state of the art for translation or summarization, they use different model architectures. And sometimes it's very hard to reconcile these two because you have done many task-specific traits and design choices on one task, and it's hard to really add a new task on that. And if you take into account the fact that many NLP tasks have different formats to have as an input, it becomes even more of a challenge. For example, question answering takes as an input a question, a context, and as an output an answer. So you have two inputs, which is very different from translation and others. And also, that's the second point, something that was actually surprising for us in the beginning when we started working on that, is when you train two different tasks are not completely related in the same model, they can interfere destructively and they can reduce performance in both of them. And I'm saying surprising because the general wisdom in deep learning before was that more data equals better performance, even if you're having tasks that don't work the exact same way. You can still learn useful things and useful cross-task knowledge, especially if they both use the same kind of input, like the same language or same kind of reasoning on the meaning of words. And so we've tried to solve a first part of that issue, which was merging all the architectures together about 3 years ago with the dynamic memory network at our team. So this network at the time got very good state-of-the-art results on question answering, pattern switch tagging, and sentiment analysis, all of that using a single model architecture. And it could also be explained to more tasks like translation, summarization, even though it didn't get very good results on that at the time. So the way it works, we have rephrased every single NLP problem as a question answering problem, where if you train to do question answering, of course, you have question and input. But if you want to do sentiment analysis, you create a new question that is, what is the sentiment of this text? Same for part of speech. You can ask, what are the part of speech of this text? And so here you can have the recurrent neural networks that are used in many parts of the model. And here this is a multi-step attention module. That's a bit similar to the one I've shown, except this is recurrent and does multiple attention steps, especially when you want to do reasoning over multiple sentences for question answering. You want to pay attention to different parts of the input before giving your final answer. And so this was indeed a very big step towards multitask. Unfortunately, when we tried to train all of these tasks together, the performance wasn't as good as we hoped. So it wasn't completely multitask at this point yet. But just recently, my colleagues Brian McCann and Nitish Keskar came up with the multitask question answering model, or MCAN. So what they try to solve is actually a bit more ambitious. They try to solve 10 different unrelated natural language tasks into one single model and one set of weights. So you can see all of the tasks here. Some of them you have the intuition they may help each other, but some of them you may have no idea how they can even fit in all of that. And so again, here you have the challenge of fitting both the model architecture and the question answer format. So they have taken the same kind of format as before with question, context, and answer. And one important point when you generate the answer in the model is that you have three choices. You can either point towards in the context, in red, point towards in the question, which is very useful for classification task. As you can see, you can ask the question, is a sentence positive or negative for sentiment analysis. if you want to make your model performant, you want it to be able to point to one of the words in the question to give the answer. And finally, the last option is to generate completely new words from scratch, which is what we want for machine translation, for example. So as you can see, depending on the task, the strategy used is a bit different. And this is not set by hand. This is what the model has learned after having seen all the examples of all the tasks at the end. And so in addition to this whole design choice, they have also added many different layers and traits from different state-of-the-art models and put them in a single encoder decoder framework. So here to go over briefly, they have the same kind of attention that we had before, except they have attention in both directions and how to change the question based on the context and vice versa. They also use the transformer layers. I think somewhere in there they have a transformer layer, which recently has come up as an alternative for recurrent networks, and that has obtained state-of-the-art in translation. And then in the decoder here, you can see the triple pointer architecture that allows the model to refer either to the question, to the answer, the question context, or make its own answer. And so this model obtained pretty good results on all of these tasks, but actually training on all the tasks at the same time boosted the performance on zero-shot relational extraction and on question answering as well. And what we also saw is that it can transfer to new domains without any new training data, which is called zero-shot domain adaptation. So that was a pretty exciting result as well. And finally, this is just an ongoing challenge. Like if you want to make your own model that can solve all of these 10 tasks at the same time, you can go to dknlp.com and submit your model, and then there will be a leaderboard to keep track of the best models with what's called a DK score that combines 10 metrics for these 10 tasks. So this is still a pretty promising development, but there are still some challenges to have in this MultiTask learning. Like for example, I've shown that in 2 tasks we obtain better performance, but ideally what we want is to have better performance on all the tasks, that to have no destructiveness whatsoever. And that's still something we haven't achieved, at least when we take that many tasks, of course. And another hope that we want to have is to have more of these zero-shot knowledge transfers. Like for example, if you train a model for translation from like English to French, and you also train it on sentiment analysis in English, can it do sentiment analysis in French without any trained data? That would be exciting, and I think that's still a work in progress that any of you can work on. But beyond multitask learning, one really true step towards general AI, in my opinion, is unsupervised learning, which fits a bit more closely what we see in the real world, where we have data all around us, but we don't really have label or ground truth attached to each of these data. Humans are very good at taking advantage of that. We navigate in the world without constant supervision, and we do fine. But for most computers, having supervision is still the best way to perform well. So since we have so much data, what can we do with it at this point? So if we go back to the Encoder Decoder framework, we can take the example of machine translation, where you have input words and output words with different RNNs. And as I've mentioned, you train these kinds of sequence frameworks by having the ground truth output as well, and then comparing word by word, and then changing your model weights to make the output as close as possible as the ground truth. But do we really need to have the ground truth every time? So I'm going to show you 2 papers that came out recently out of Facebook research that I think are pretty impressive in that respect. One of them does translation of word by word from one language to another without any supervision. And the other one extends that to whole sentences. So first, unsupervised word translation that came up, I think, earlier a few months ago. So if you go back to the word vectors that we described before, you can try to plot them in a 2D or multiple dimension space. And then you can do that for different languages at the same time. You can do that, you can have like one word vector distribution for English, and then let's say another one for Italian. But at this point, they have nothing to do with each other. All you can tell is that there are some clusters in both languages that seem to represent the same things. Like you can imagine that all words related to like animals will be in one cluster in both languages, or the direction of singular to plural will be the same too. And so the idea of this paper that tried to connect which words in which language correspond to other language The idea is that each of these languages have a latent structure that is the same, and so we're trying to recover that structure by merging these two distributions, make them as close as we can together. So it does that in 2 or 3 steps. The first one is to learn a rotation matrix W to transform one of the distributions to make it look as close as we can as the other one Y. And this is done through adversarial training, which is, let's say you have one agent that picks a word at random, another one tries to predict whether that word came from English or from Italian. And what the first agent is trying to do is to fool the second one and making the distributions as close as possible to be indistinguishable. And once this is done, adversarial training is pretty noisy, so we need a refinement step to make them even closer to each other. So this is done through the Procasys algorithm that actually tries to just make distributions close, assuming that you know the correspondence between some of the words. So it just assumes that the closest words to each other are the ground truth and then tries to make the distribution closer to each other. And finally, you can recover the translation that you've learned by nearest neighbors from the two distributions. So there are more results in this paper, you can take a look at it, but one of the most impressive ones is if you look at Italian to English, the unsupervised precision is actually very close to what you would learn through supervision. Let's say, imagine you have English and Italian sentences that mean the same thing. You can learn a model to learn the word meanings, and you wouldn't do much better than if you had no supervision on which words mean what and which sentences mean what in English and Italian. So even though it's a pretty good step, we still need to find a way to scale that to full sentence translation, and that you can, yes?
If it's just mapping words to words, how does it account for like the structure of the sentence, like stuff that are different in different languages?
I'm gonna talk about that next. Like this paper only concerns about words, but yes, it's a very good question. So from the same team at Facebook, they came up recently with this paper, unsupervised sentence translation, that uses different models. So they're not the first ones to do this, but this paper has been laying down some 3 principles that I think will be required to make fully unsupervised sentence translation possible. So these 3 principles are initialization, start with a good model, language modeling, where you want to know what every sentence should look like as a translation, and then back translation, which I'm going to go in more detail after. So first, initialization. You can imagine that translation search space is enormous, and so it will greatly help your model if you start with a model that does good on some words. Like it doesn't have to be perfect, but at least if you translate one sentence approximately, it will still have some words or sub-word units correct. So we can use actually the paper that we've just shown earlier to do unsupervised word translation as a start. Or if your languages are very close to each other, you can also decompose words into sub-word units and assume that the original sentence is a translation, and you will have some sub-word units correct. So where do you go from there? Well, you don't have supervised meaning for the sentences, but you do have lots of data for each language. And what you can do in that case is do language modeling. So in that case, it's a bit different from earlier where we tried to predict the next word based on a sequence of text. Here, the language model is trying to, given a noisy sentence, reconstruct a clean sentence. As for example, you have a sentence in English where you remove words and flip them randomly, which is what may happen if you do word-by-word translation from another language. And given that you know what English should look like, you're trying to reconstruct that, which means that if you start from the previous model, when you do word by word, you will be a bit closer to what a real translation will be like. But it's still not perfect. Once you have that, you can actually do iterative learning with back translation. So back translation has been a method used for semi-supervised learning in MT, which means you have some parallel data of, let's say, French and English for the same meaning, but you also have, for some languages, data with no translation. And you can still make some good use of that by taking one sentence in one language, translating it to the other one, and then with a second network, translate it back to the first language, which means that if you take the first text you started with, this is actually, in a way, a supervised label for the last translation. And so you can use that to train your model, and you actually fall back on the supervised learning framework that we discussed before. And so how well does this do? Well, it doesn't do as well as fully supervised translation, unfortunately, but it does get some things correct, as you can see on these two examples. Here on the first one, from French to English, you can see it's flip-flopping a little bit in the use of prepositions from in or into, but then most of the words are actually quite correct. And you can see that by default, it does use a French order for pH neutre, but then learns to flip it later to neutral pH. What I find interesting, though, is a failure case of translating langue to language, because langue also means tongue in French, but the model has no way to know that at this point. And same here, you can see that the sentence with two different models is pretty correct. Again, we never told the model how a translation looks like in the first place. What's interesting is that it translates Batman to Wolverine at first, but then corrects itself later on. Not sure why it does that, but that's a pretty interesting thing to see. So yeah, there's still a lot more to do in that domain. That, for example, do we actually need these three principles? Because they are not strict, well-defined theorems. They are just guidelines that the authors think are what we need for a good unsupervised system. But maybe we can either come up with more principles or replace them. Of course, how to improve performance. Like, is it even possible to match the supervised learning performance with this? Next few years will tell us, I guess. And finally, something that I find particularly interesting is, can we scale this approach to new NLP tasks like summarization? I think it's going to be a bit of a challenge, because one of the principles is batch translation, which means you are able to convert your input from one domain to the other back to the first one. And for summarization, you cannot really do that because you are reducing the scope of your input. But maybe if you use auxiliary tasks or more data in different ways, it might be possible. So yeah, of course, I left out many different areas of deep learning for NLP, like speech recognition, question answering, and we can go in more details in this, but I hope this has inspired you to go out and explore more of deep learning for NLP. And if you have any ideas, any questions, feel free to ask me after the talk. And we are hiring full-time and interns to work in Palo Alto, California. Thank you. Right. Any questions? Yes?
Where did you get the training data from that you used?
For summarization?
Yeah.
We use the CNN and Daily Mail news articles. For each of them, humans have written bullet points. This is similar to what I've shown in one of the slides when I was introducing summarization. Right here. So from CNN and Daily Mail news articles, we took these bullet points and concatenated them to provide a multi-sentence summary as a ground truth training. So we had about, like, I think 300,000 to 400,000 summaries, which allowed us to have pretty big models. Yes?
So the attention modules that you mentioned in your Extractive summarization paper and the multitask paper, do they work well when the articles become very long?
Yeah, that's why they work so well, is because they can scale to news articles that are as long as we want. I mean, we did limit the length of the news articles to 800 words. Most news articles don't go further than that. But yeah, I do assume that if we ever want to do summarization of multi-page documents, we may need a more refined attention system. Yes?
Talk a little bit more about your embedding techniques.
About what?
Embedding techniques? Or embedding techniques?
In which parts?
In your early feature when you were associating the words with certain connotations of feature labels.
Oh, and the very beginning? Oh yeah, sure. So there are many ways to learn these word embeddings, and one of the main ways that has been used by Mikolov et al. Was skipgram prediction, where given a word, you train to predict which words are surrounding that one, like the two ones before and the two words after. The intuition is that if you replace your central word by another one with similar meaning, you will try to predict the same ones. So you can do this in an unsupervised way because you only need the sequence of words to train that task. But you can also learn task-specific word embeddings. If you just start with a model like this, you can initialize these word embeddings at random, and they will learn to express a meaning that's very specific to what you're trying to solve. Yeah. You had a question too? Yeah.
So we talked a lot about the different accuracies between the supervised and unsupervised model.
Mhm.
I was also kind of curious about like the speed of these different models.
That's a good question. I'm actually not sure if the paper goes in detail into that. I'm assuming that the speed is not that much different. If we go back to the results here, they only do like 45 epochs of a neural MT model, which is within the expected range of supervised training. But the model itself is actually very similar to supervised one, just the way it's trained is different. Yeah. Yes?
I'm just kind of curious, how robust are these models in handling things like humor and sarcasm?
That's a very good question. That's still something that was hard to encode in the beginning of NLP and still hard to encode these days. Even if you train a model that's specifically trained to detect sarcasm, I don't think we've done as close as humans have, mainly because there aren't that many examples of that. And many examples do require context to really understand. And I think right now I've only shown models that take into account a single input without very clear defined context. So I'm assuming once we do have a very complex reasoning over like cultural knowledge bases, and once you put sarcasm into play, you might get some progress, but that requires way more input than we have. Yes?
How do you decide when like a particular paper has like made significant enough contributions that it's worth incorporating it into the model that you're using?
It's very task specific in the end. It depends of how much of a bump in accuracy that model provided. Like for example, the transformer network that I've briefly mentioned, that's an alternative to RNNs. They have a huge bump in both accuracy and in speed. So we felt like if we had to train a model that has 10 times the data, speed was a huge factor for us. Mm-hmm.
Let's give a round of applause to thank Romain.
Thank you.
If you guys have any other questions, he'll be outside, or you can head downstairs for the keynote speaker talk. Yeah. Thank you.